Welcome everyone to my channel. Let's start the question number 51. The correct shear force diagram for the beam shown below is. So as per the question, the simply supported beam hinged at support A and roller supported at end B is subjected to a central move and clockwise movement at here. Suppose this point is C and total length of the beam is 10 meter. Okay, so first we have to determine the reaction at both the support. At support A the reaction will be RA, and at support B the reaction will be RB. Let's assume. Okay, so now as the beam is in equilibrium, we can use the formulas. All the moments about this plane is equal to 0, so taking moments about the point A is equal to 0. So if we take moment about the point A equal to 0, we have only RB, this force and this moment. Okay, so RB into this length 10 meter from RB to A, so minus RB into 10, minus because RB is trying to rotate in anti-clockwise direction, so minus RB to 10 plus this moment is clockwise, so plus 10 this force into 10 centimeter, that is 0.1 meter. So this moment will be 10 into 0.1 will be equal to 0, total will be equal to 0 as there is no other forces or moment. So if we calculate, we will get RB equal to 0.1 ton, and we also know that by the equilibrium all the forces in vertical direction is equal to 0. So reaction RA plus reaction RB equal to 0. We know if reaction B is equal to 0.1 ton, then reaction ARA will be minus 0.1 ton. Okay, now moment, as this is a simply supported beam, the moment at the end, at the support end A will be 0 and at the support end B will be 0, because support A is hinge support and hinge support cannot take moment, and support B is roller support, it also cannot take moment. So both moments at A and B will be equal to 0. Now all the moment will be calculated at this point C. Moment at C, if we are coming from A, at point A moment equal to 0, but at point C just left, when the clockwise moment at center is not involved, so the moment at C will be RA into 5. So RA equal to minus 0.1 into this length is 5 meters, so 0.5 ton meter, and the moment just right of C when this clockwise moment at the center is involved, so the moment at C will be 0.5 minus 0.5 plus this clockwise moment 10 into 0.1. 10 ton is the force and 10 centimeter vertical is the distance, so moment equal to force into distance. So if we calculate MC just at the right of C will be 0.5 ton meter. So now we will draw the bending moment and shear force diagram. For shear force diagram, suppose this is the baseline. Okay, so RA is minus 0.1 ton, so we will take this line to minus 0.1 ton. Suppose this is minus 1, and this line will be constant up to B. Now reaction at B is 0.1 ton, so plus 0.1 ton minus 0.1 ton equal to 0. So the reaction will be at here. This is the shear force diagram, and bending moment diagram will be at here bending moment 0, at here bending moment 0, and moment just at left of C will be minus 0.5 ton meter, and at the just right of C will be plus 0.5 ton meter. So option A is right answer. By the shape of the rectangular shear force diagram we can understand, but the option is slightly wrong. It will be 0.1 ton instead of 1 ton. Question number 52. The correct bending moment diagram for the middle column of the frame shown below is. There will be no moment, no bending moment in the central column. Okay, so the bending moment diagram will be simply D. Option D is right answer. Question number 53. The reaction at support A of the propped cantilever beam shown in the figure 12.7 is. Suppose this is our propped cantilever beam subjected to a point load 1 ton at B. Now let's consider the beam AB as a cantilever beam. Okay, where there is no vertical prop at end B. Okay, the beam is subjected only the downward load 1 ton at B. Okay, so we know by the cantilever beam deflection formula, the deflection will be PLQ by 3EI at end B. Similarly, now if we consider the cantilever beam subjected to upward load, that is prop at end B, but there is no downward load 1 ton. Okay, so the deflection under the upward reaction at B will be RB into LQ by 3I, and RB is the reaction at the prop. Now we can equate the downward deflection is equal to the upward deflection of the beam as the beam is in equilibrium. So by equating equation 1 to equation 2, we get RB equal to 1 ton. And as the beam is in equilibrium, we also know summation of all the force in vertical direction is equal to 0. So RA plus RB equal to 1, because this only load exists here on this beam, 1 ton 1 ton. So RB equal to 1 ton, so RA will be equal to 0. Option A is right answer. Question number 54. As shown in the figure 12.8, for unyielding supports, the slope deflection equation for part BC of the beam shown in the figure. So for this span, the moment at B MBC will be equal to moment fixed end moment at B for this span plus 2EI2 by L2. This is L2 and this is I2 into within bracket 2 theta B plus theta C. Theta slope at here plus slope at here. Okay, because this span is considered, option A is right answer. Question number 55. For this figure 12.9, what is the degree of static indeterminacy of the structure? This is a rigid frame, so we know the formula for degree of static indeterminacy for this structure. ds equal to 3m plus r minus 3j. M is the number of member for the frame, r is the number of reaction components from the frame, and j is the number of joints. So number of member will be 2 1 2, and number of reaction components will be 3 plus 3 6. 3 means at this end the reaction will be 1 horizontal, 1 vertical and 1 moment, and at this end the reaction component will be 3, 1 horizontal component, 1 vertical reaction component and 1 moment. So 3 plus 3 equal to 6. R will be R equal to 6, and J is the number of joint 1 2 and 3. J will be equal to 3. So if we put all the value, we will get ds equal to 3. Option C is right answer. Question number 56. What is the degree of kinematic indeterminacy of the beam shown in the figure 12.10? For this beam, we have to determine the degree of kinematic indeterminacy. So we know the degree of kinematic indeterminacy for this beam will be 3j minus r. So j is the number of joint. Number of joint will be 1, 2 and 3, and r will be equal to one reaction component from this roller supported end, one reaction component, that is vertical component, from this end, and two reaction component, one horizontal and one vertical reaction component from this end. So 2 plus 1 plus 1, that is equal to r equal to 4. So if we put the value into this equation, we will get dk equal to 5. Option D is right answer. Question number 57. What is the degree of kinematic indeterminacy of the beam shown in the figure 12.10 if the axial deformation is ignored? The formula for degree of kinematic indeterminacy for this beam will be 3j minus m plus r plus summation of r dash. This will come into play when the beam is involved with internal hinges. Okay, so this one is out. So j is the number of joints for the beam, m is the number of members of the beam, and r is the reaction components from the beam. So j will be equal to 1, 2, 3, and m will be equal to 1, 2, and reaction components will be 4. One vertical reaction components from this end, one vertical reaction components from this end, and one horizontal and one vertical reaction components from this end. So r will be equal to 4, and if we put all the value into this equation, we will get dk equal to 3. Option B is right answer. Question number 58. What is the degree of kinematic indeterminacy of the frame shown in the figure 12.11 if the axial deformation is ignored? So for this figure, that is rigid jointed frame, the degree of kinematic indeterminacy when axial deformation is ignored or neglected, the formula for kinematic indeterminacy dk will be equal to 3j minus m plus r plus summation of r dash. This one is out because this one will come into play when the beam or frame is involved with internal hinges. I will show you later. The rest notations are j number of joints. Number of joints will be 1, 2, 3, 4, 5, 6. J will be equal to 6, and the number of members will be 1, 2, 3, 4, 5, 6. We know at the hinge supports two reaction components occur, one vertical reaction and other horizontal reaction. So 2 for this hinge and 2 for this hinge, so r will be equal to 4. If we put all the value into this equation, we will get dk equal to 8. Option A is right answer. Question number 59. What is the degree of static indeterminacy of the beam shown in the figure 12.12? So for this beam, the degree of static indeterminacy formula will be 3m plus r minus 3j minus summation of r dash. M is the number of member, r is the number of reaction components from the beam, and j is the number of joints, and r dash is the number of additional equation required due to internal hinges or hybrid joints. The formula for r dash will be equal to n minus 1. N means the members which are connected with the hinges, so n will be equal to 2. This member and this member are connected in this hinge. 2 minus 1, r dash will be equal to 1, and m is the number of member will be 1, 2, 3, 4, and j number of joints will be 1, 2, 3, 4, 5. J will be equal to 5, and number of reaction components will be one vertical, one vertical, one vertical, and 3 at this fixed end. So total reaction components will be 6. Now putting all the value into this equation, we will get ds equal to 2. Question number 60. Look at the frame. One load W is over this frame at the side, at the right side of the frame. Okay, the frame that is rigidly connected at both end. This is fixed end, this is fixed end. So the question asked here, the portal frame shown in the figure 12.13 will sway or not sway, in which direction the frame will move. Look, the frame is unsymmetrical with the load, so the sway will come into play for the frame. So as the load at the right side of the frame, so we can clearly say it will sway towards the right. Option C is right answer. Question number 61. Due to uniformly distributed load, maximum reaction at support B for the beam shown in the figure 12.14 will be when? For this beam we have to calculate the condition, the loading condition, when the reaction at B will be maximum. So let's calculate and determine when span AB is loaded. Okay, suppose this span is 3 meter and this span is 2 meter. This is over one end overhang simply supported beam. Say the beam with span AB is subjected to a uniformly distributed load 4 kN per meter, and the reaction at A is RA and reaction at support B is RB. If we take moment at A, so summation of all the moment equal to 0 at this point by the equilibrium. With respect to this point A, the reaction at B, RB, is trying to rotate in anti-clockwise direction. So RB into 3, this is minus, plus the load is trying to rotate in clockwise direction. So 4 into 3 into 3 by 2 equal to 0. After calculating, we will get RB equal to 6 kN. So reaction RA plus reaction RB equal to the downward load 4 kN into the span 3 meters. So 12 kN, and we got RB equal to 6 kN. So RA will be equal to 6 kN. Now when the span BC is loaded, the reaction at A is RA and reaction at B is RB. And where BC span is loaded with the same loading intensity 4 kN per meter, and by the equilibrium, if we take moment about the point A, so summation of moment equal to 0 at the point A. Now if we take moment at this point, the reaction force is trying to rotate in anti-clockwise direction, so RB into 3 but minus direction as it is anti-clockwise, plus the load which is trying to rotate in clockwise direction with respect to point A. So this bending moment will be 4 into the span 2 into the center of the span is 2 by 2 plus distance from the center of the span to the point A will be 2 by 2 plus 3 equal to 0. So if we calculate, RB will be equal to 10.67 kN, and as RA plus RB equal to the total loading intensity 4 into 2 equal to 8 kN, as we got RB equal to 10.67 kN, then RA will be equal to minus 2.67 kN. When the span AB and BC is loaded, entire span ABC is loaded, then the scenario will be reaction at A RA and reaction at B of the beam is RB. So by the equilibrium, if we take moment about the point A equal to 0, then the reaction RB is trying to rotate in anti-clockwise direction, so minus RB into 3 plus the downward load trying to moving in clockwise direction plus 4 into 5 total distance into half of the loading span 5 by 2 equal to 0. So RB will be equal to 16.67 kN, and RA will be equal to total loading 4 into 5 this span minus 16.67 equal to 3.33 kN. When span AB is loaded, RB equal to 6 kN. When span BC is loaded, the reaction RB equal to 10.67 kN. But when the entire span AB and BC is loaded, the reaction value RB will be equal to 16.67 kN. So it is maximum. So maximum reaction at support B will be when the entire span ABC is loaded. Option C is right answer. Question number 62. The influence line for force in member DC of the truss shown in the figure 12.15 will be. As per the question, the unit load will be at C. Okay, so the forces in the member DC, a member of the truss, will be 1 unit. The influence line diagram of this member DC will be triangular in shape. Okay, this is the ordinate of the triangle will be 1 unit, because the force in the DC member is 1 unit, and force at this point is 0 and force at this point is 0, and ordinate of this triangle at 1 unit. Okay, so if we connect all the point through the straight lines, then we will get this shape. So option B is right answer. Question number 63. In the beam shown in the figure 12.16, if the displacement at C due to load W at B is 5 mm, then the displacement at B due to a load of 0.2 W at the C will be. As per the question, suppose this is the simply supported beam AD. Okay, and this is coordinate B and this is coordinate C. Coordinate means the node point. So at the coordinate B, the beam is subjected to a point load W, and for this load at the coordinate C the deflection is 5 mm, and for the same beam when the beam is subjected to a point load of 0.2 W at the coordinate C, then we have to determine the deflection at the coordinate B. By the reciprocal theorem of Maxwell, we can write this load into this deflection and this load into this deflection, and these two can be equated to each other by the theorem of Maxwell. Suppose deflection for the second case here at coordinate B is x mm. Okay, so W into x equal to 0.2 W into 5. By calculating we will get x equal to 1 mm. Option A is right answer. Question number 64. The flexibility matrix corresponding to coordinates 1 and 2 for the structure shown in the figure 12.7 is. For question number 64, the continuous beam ABC is given. The support B is regarded as coordinate 1 and support C is regarded as coordinate 2, and at support B moments are applied at the both ends, and at support C moment is applied from one end, that is in anti-clockwise direction, and flexibility matrix relates the displacement, that is moment or force, due to a unit force applied at a coordinate. But in simple language I will tell you, flexibility is the simply the rotation value, the slope at different coordinates due to unit moment or unit force at a certain coordinate. And when the value of flexibility is arranged in a matrix, then it is a flexibility matrix. So by the application of external moments at coordinate 1 and coordinate 2 for the beam, the rotation diagram or the deflected shape by the moment will be like this: theta at support A, theta at support B from the span AB, and theta at support B from the span BC, and theta for support C or coordinate 2. And theta is the slope at designated supports. Now let's take an example. Okay, when a simply supported beam subjected to a moment at this support, suppose PQ is the simply supported beam and the support P is subjected to a moment, then the slope at P will be ml by 3 EI and slope at Q will be half of this slope at P, so ml by 6 EI. Now we will determine the flexibility matrix for this beam structure. So flexibility matrix is the square matrix. Okay, so for this two coordinate 1 and 2, the square flexibility matrix will be F11, F12 and F21 and F22, that is 2 by 2 square matrix, 2 rows and 2 columns. F11 is the flexibility at coordinate 1 due to unit moment applied at coordinate 1, and F12 is the flexibility at coordinate 2 due to unit moment applied at coordinate 1, and F21 is the flexibility at coordinate 1 due to unit moment applied at coordinate 2, and F22 is the flexibility at coordinate 2 due to unit moment applied at coordinate 2. So now we will calculate the value, flexibility value F11. F11 means is the flexibility at the both ends of support B, that is at coordinate 1, because moment applied at both ends. So theta plus theta equal to 2 theta. So slope will be 2 times at the coordinate 1. So the value of theta at this end at coordinate 1 will be ml by 3 EI, but as it is 2 theta or moment applied twice, so the value will be multiplied by 2, so 2 into theta, that will be equal to 2 ml by 3 ei. Now we know unit moments flexibility value is determined considering the unit moment, so m equal to 1, so f11 will be equal to 2l by 3 ei. Now f12 will be half of the theta, half of the theta value at here. So at this coordinate theta value is ml by 3i. So at this end, at this coordinate, due to unit moment at this coordinate, the theta value will be theta by 2, this theta by 2, so half into ml in by 3 ei, so ml by 6 ei, m equal to 1, so l by 6 ei. Now f21, first we will calculate f22 when unit moments are applied at coordinate 2 and flexibility is also determined at coordinate 2, so it will be theta. Okay, so theta value we know where moment is applied, so theta will be equal to ml by 3ei, as m equal to 1, it will be equal to l by 3ei. Now f21, that is the flexibility needed at coordinate 1 due to unit moment applied at coordinate 2, so that will be equal to half of this value theta, so half into ml by 3ei, so as m equal to unity, so f21 value will be equal to l by 6 ei. Now putting all the value into this flexibility square matrix, we will get the flexibility matrix value for the beam structure is L by 6 ei common, and the matrix will be 4 1 and 1 2. Question number 65. The elements of flexibility matrix of a structure are dependent on the choice of coordinates. Option A is right answer. Question number 66. Study the following statements. Let me give you a short idea about the force method and displacement method of the structure. We all know the difference between determinate and indeterminate structures. The structures which cannot be solved by the equation of equilibrium is known as indeterminate structures, and the structures which can be solved by the equation of equilibrium are known as determinate structures. And the basic equilibrium equations are: in a plane, summation of all the moments about any point is equal to 0, summation of all the horizontal force is equal to 0, and summation of all the vertical force is equal to 0. So to analyze the indeterminate structures, both force method and displacement method of the structures are utilized. In the force method of analysis of indeterminate structures, the unknowns are force or moment, while in case of displacement method of analysis of indeterminate structure, the basic unknowns are nodal displacements. Displacement means translation and rotation. In the force method of analysis of the indeterminate structures, first force displacement equation are written and then the unknowns are calculated from the compatibility criteria. On the other hand, in case of displacement method, first force displacement equation are written and the unknowns are calculated from the equilibrium equation at the joint. Both the force method and displacement method of structures are used to analyze the indeterminate structures. Okay, but the way is different. Statement 1. The displacement method is more useful when the degree of kinematic indeterminacy is greater than the degree of static indeterminacy. In displacement method, the degree of kinematic indeterminacy is less than the degree of static indeterminacy. So this statement is wrong. Statement 2. The displacement method is more useful when the degree of kinematic indeterminacy is less than the degree of static indeterminacy. Correct statement. Statement 3. The force method is useful when degree of static indeterminacy is greater than the degree of kinematic indeterminacy. No. Incorrect statement. Statement 4. The force method is more useful when the degree of static indeterminacy is less than the degree of kinematic indeterminacy. Correct statement. So the correct answer will be statement 2 and 4. Option D is right answer. Question number 67. Select the correct statement. Statement A. Flexibility matrix is a square symmetrical matrix. Right. Statement B. Stiffness matrix is a square symmetrical matrix. Right. So option C is right answer, both A and B. Question number 68. To generate the jth column of the flexibility matrix, a unit force or unit moment is applied at coordinate j, and the forces are calculated at all the coordinates. Option C is right answer. Question number 69. For stable structures, one of the important properties of flexibility and stiffness matrix is that the elements on the main diagonal stiffness matrix and flexibility matrix must be positive. Of statement 1 and statement 3, option A is right answer. Flexibility matrix is the force method of the structure, whereas stiffness matrix is the displacement method of the structural analysis. Flexibility matrix is the inverse of stiffness matrix, and stiffness matrix is also the inverse of flexibility matrix. Question number 70. The strain energy of a structure due to bending is given by. Option B is right answer, half into integration m square dx by ei, where m is the bending moment at a section x and ei is the flexural rigidity of the structure. Question number 71. The effect of shear force and axial force on plastic moment capacity of a structure are respectively to. Actually, the presence of shear force will reduce the plastic moment capacity of a section, as shear force will consume some of the yielding strength of the material, leaving less capacity available to resist the bending moment. And if you see, axial force will also reduce the plastic moment capacity, because when the axial force is present, a portion of the cross section will be used to resist the forces, reducing the area available to resist the bending moment plastically. So plastic moment capacity will reduce in effects of shear force and as well as axial force. Option D is right answer. Question number 72. For the structure shown in the figure 12.18, the ratio of relative stiffness for AB and member AC is. Question number 72. The structure is drawn here. We need to find out the relative stiffness of the member AB and AC and make the ratio between AB and AC. The structure is fixed at end B for the member AB, and the structure is hinged for the member AC at end C for the member AC. So relative stiffness of the member AB of the structure will be I by L. I is the moment of inertia of the member and L is the length of the member. And for member AC, the relative stiffness will be 3/4 into I by L, as this end is hinged. Now if we make the ratio between AB to AC, then we will get the value 4 by 3. Option C is right answer, 4 by 3, where I and L represent moment of inertia and length respectively. Question number 73. When a unit rotation is given at the end A of the beam shown in the figure 12.19, the moment produced at end B will be. Now see, for this question, this is a prop cantilever beam. Okay, now for this beam at the end a unit rotation is given. Unit rotation means theta equal to 1. So by this unit rotation at the end A, the moment produced will be 4 ei by L at this end. Now this end is our near end and this end B is our far end. So when our far end is fixed, the induced moment at the far end will be the half of the produced moment at the near end. So the moment induced at the end B will be 2 ei by L. Okay. Option B is right answer. Question number 74. Which of the following methods of structural analysis is a force method? Option B is right answer, column analogy method. Question number 75. Which one of the following methods of structural analysis is a displacement method? Option A is right answer, moment distribution method.